Hello and welcome to Battery Testing is Not as Simple as Test a Battery. This Automotive News webinar is brought to you by ATS Industrial Automation. We're delighted you're with us for this presentation. I'm Mary Beth Vanderscaff, Managing Editor at Automotive News. Our speaker is Jack Porter, Applications Engineer, Technical Specialist at ATS Industrial Automation. With 40 years of industrial test experience, Jack has led and developed test processes and handling for leading automotive OEMs. Jack assists customers in improving and automating their EV battery module and assembly test processes. Over the last decade, he has concentrated on EV powertrain, power conversion, and power storage, helping OEMs increase throughput and improve EV test processes. I'll turn it over to Jack to get us started.
Welcome. I'm glad you all could join me today. And today we're going to be talking about battery testing. And the name of the presentation here is Battery Testing is Not as Simple as Test a Battery. And we're going to spend some time and take a look at that. We're going to take a look at what's going on in the market today, what's going on within the engineering community, within the production environment in terms of creating batteries as we define them today. My name is Jack Porter, and I've been doing industrial tests for a long time, as Mary Beth alluded to, and very nicely spoke of me. I appreciate that. I've been doing things mostly in powertrain, power conversion, power storage for the last decade or so, as we've been busily electrifying just about everything that's out there. Over my many years of production testing, I've been through a few battles, got a few scars to show for it. And I've learned a few things. And today, some of the things we're going to talk about that we learned has to do with battery testing. And what do you think about when you think about testing batteries? For example, if your headlamp's not working, do you pull out the cells in it and get out your voltmeter and take a voltage measurement and say, oh, those batteries are dead and put some new ones in? Or maybe if you're a little more adventuresome, you go over to your smoke alarm detector that you have to replace the batteries in and you pull out the 9-volt cell and you give it a little taste on your tongue and you feel the current tickle and you know, oh, that's a good battery. This is testing a battery. But what we're talking about today is going to be testing the batteries with respect to the electric vehicle market and grid storage, and what we need to consider and to be successful in production testing these batteries. Slide. So when we look around us today, I like to talk about the cliche that we've all heard, that the only constant is change. And sure, it's a cliche, but it's rooted in something. And today, with respect to this market we're talking about, it's certainly true. There's exciting changes going on all around us, evolving in a lot of different directions. Some of the things that we look at that are changing, we look at the baseline chemistries in batteries, we look at the end applications, be it mobility, storage, range extension. You look at what the batteries are themselves in terms of the packaging and the system connections. What are the charge and discharge requirements, and how do we get things charged, and what is it that we're discharging them into? So it's just swirling all around us. And my news feed is just filled with a stream of battery development projects, things that are going on all over the place in terms of producing batteries and installing them. We can look at large-scale grid storage installations. We mentioned the exciting chemistries, and everybody's trying to get the next big step change in battery technology, and it goes across a variety of disciplines and a variety of techniques. If you take a look as well in these quick searches, you'll see that the investment in production is widespread. There's just battery plants going up everywhere, all sorts of different types. And all the research and development in this field just continues to push the technological boundaries. And we're trying to reduce costs, reduce size, increase power density. It can be almost overwhelming. And combine this with the demands of production and all the changes and stuff. Well, how are we going to deal with this? What do we do? This is our challenge today. Next slide. So this demand is actual, but why is this a problem? Well, we like to think about it in terms of the magic triangle. And this magic triangle is trying to highlight give us a framework to be able to break down all these converging factors that are going on. We talked about all those wonderful changes that are going on, all impact us in terms of trying to do our jobs. You know, it goes across everything. So if we look at this, we kind of start from the left and look what's over there. And we talked about this a little bit already. The battery technology is improving at a rapid pace, and this has a big effect on production testing. If we look at the time that it takes to do a battery project, typical large-scale assembly projects might take 2 to 3 years from the project start, when you go out, you know, with a request for proposal, to the time that you get up to full-scale production. And those kind of timelines are just too long based on the demand. The demand is here today. What changes do we need to make in order to increase our ability to compress that timeline? Additionally, we throw on top of that the changes. And so now we're moving up to another leg of the triangle, right? And these changes make the project a moving target. You know, and how do we determine how it is we transition a manufacturing space to reach a full production in a shorter time frame, but without the mature technologies and processes? We're used to a slower pace where we go through this process and go through prototypes and pilot builds, and then further testing, and then we go to commercialization and start to scale up production. And we don't have time for that anymore. And so we have this convergence of these disciplines, perhaps, that have not been assembled together before. So I said, we got new technologies, we got all these different things that are going on. And maybe we have groups within our organization, or we need groups from other organizations in order to bring this together and pull it off. Traditionally, we've leveraged historical gains in manufacturing efficiencies. We've taken what we learned in the past and brought it forward, and we've had time in order to let that roll forward. How do we gather the good that we got out of those historical gains and bring them into today? And now we start moving into the third side of this triangle, which gets into flexibility and how do we do things in order to be able to adapt to the pace of change and the high demand. And this is what we need to do within our organizations in order to ensure our success. And just to kind of sum it up, despite not being a brand new industry, batteries have been made for a long time, but battery manufacturing is not a solved problem. Next slide. So what I'd like to propose is that a shift in perspective is required. And if we look at here, we kind of see the things that I think we need to take a look at and change our perspectives on some of these things in terms of how we go about this in order to achieve our ET targets. What can we do to ensure our success? So the challenges in battery manufacturing exist in a number of commercial and technical areas. So we're going to have to work in those areas if we're going to do a shift. If we look at what we have here in terms of capacity, domain knowledge, and project management, and excellent scalability, these are the people we have today, and they're good people, and we know them, and we know we do well. But the question is, can they do well for what we need going forward in our battery testing? Do we have the need for new approaches to our testing requirements? And so I would say let's start with what we have and focus on areas for learning or for modifying or enhancing what we have. So it's kind of like, how do we build ourselves up? How do we shift into this? And this is where the shifts come on in. We go to the passionate teams. We kind of start moving around in our perspective. And this is, how do we handle the timing factor? And this gets into the possibility and the capability that we highly recommend in terms of working with somebody else to help you. This comes into collaborative original equipment manufacturers like ATS. How do we develop our supplier relationships? And we all know what's happening in supply chains today. How do we make that do something good for us? How do we become the person that is the key? What do we need to do to work back and forth? And one of the things that's historically been kind of a stumbling block is the trusting portion of this, right? In terms of getting dedicated people to help you, to be embedded within your organizations, to act as an adjunct to you in order to be able to bring these things to fruition. And the whole point of this is to be able to respond to the changes and to do it quicker. And then as we look towards a little bit further downstream, and this is where we bring in the future proofing, what do we need to do today or consider today in order to be able to handle the change as it's occurring? We look at, and like I say, all these components are things we kind of know today, but it's a question of taking a deeper look and realigning this in order to be successful in the battery testing. We know we make best-in-class components, and we know we use digital capabilities in terms of simulation and artificial intelligence in spots. What is it that we need to do today in order to be successful as we go through this rapid change going on? Scalability and modularity are two big keys, and those are always difficult, especially modularity. In terms of how do I do that? You know, where do I make those trade-offs between upfront costs based on projected downstream modifications? How do I come up with something today that is going to stand the test of time and be able to handle the changes that are coming to us? Slide. So one of the ways to do that is we kind of sum it up here by saying simultaneous, not parallel. And if we go to Webster's is going to tell us that simultaneously means occurring at the same time, exactly, coincident. Whereas parallel is everywhere equidistant and not meeting. And I think a lot of times we tend to think about things being parallel processes. And that's good. We have things that are going on at the same time. But the key thing here is we need to have these things meet. We must meet during the development, during the prototype, during the product launch. So perhaps going back to organizations and the shift in perspective, people in the laboratories coming up with the baseline chemistries or materials to be used or figuring out the sequences for charging and discharging need to be talking to the people that are going to have to build these things and need to be talking to the test people in terms of what do we do when we finally get this thing built. We take a look at across platforms, and this is another avenue to go in there. We look at especially when we look at the electric vehicle market, we're trying to come up with battery packs that we can put into multiple applications or perhaps even on different platforms. And this is common in a lot of parts within mobility segment right now. The difference here is in terms of we've got this forever changing part, and the end functionality is the same, but the format and perspective that is within it is changing. And how do we get that so that I can apply it, maintain my testing that I'm doing, and be able to broadcast that across and be able to produce the various things we need? We kind of sum it up at the bottom of the slide. It kind of says that everyone's innovating and trying to standardize at the same time. And this is not an easy task, but that is our task that we have today. Next slide. Looking at it a different way, let's look a little more specifically. We've got evolving battery parameters. And if we look at some of these, we highlight some of the areas that are changing. We've alluded to some of these, but take a little closer look at them here. So we've got product changes. So I look at two different sides of this. We've got the things that are happening on the product that are going to affect us, and then we have the things that are happening in testing in terms of how we prove what it is that we built is good and we should ship it to the end user. So the chemistry, lots of activity there. Sometimes this may not have such a radical effect in terms of what we're doing in the production testing, and yet if you break down the production testing across the realms, it may be that there's certain pockets this hit. Maybe this hits up earlier in the process than it does downstream as these modules build and evolve. Something to think about with respect to the baseline chemistries that you're using. Packaging is something that is evolving rapidly. And once again, it comes to your end application in terms of what it looks like, in terms of what the modularity is within your system, how big it is, what environment it's going at the end. And the interconnections are a big thing with that as well, in terms of eventually all of these need to be plugged in to be charged and need to have a load on them to discharge. And what is that? How is that hooked up? How is that terminated? Is it permanent? Is it something that comes and goes? Are there portions that are permanent, portions that come and go? So a little variety there. What is the product we're testing doing? What do we need to do in testing to ensure that's all going to work for the situation that it's living in? Monitoring is a real big area because this is where we have some intelligence. So once we get up past a battery cell and we start to string a few of them together, or weld a whole thousands of them together, we start putting some intelligence on these parts. And we do that for a variety of different reasons. Some of it so we can know status of the part. Some of it is to monitor for issues with the part. Some of it is to preserve and maintain the overall life and performance history of the part. And so that's continuing to change as well. Lots of change going on here. Some of that is buried in a lot of that actually is buried in the software. And how do you handle and respond to all of that? You get a plethora of data, and what do you do with it? What do we do with it in test? How do we use it? How do we not use it? And of course, safety. Lithium has its own unique characteristics, thermal-wise. Other battery chemistries perhaps do not. But at any rate, the very act of charging and discharging across all chemistries seems to create heat. And what do we do with that heat? How do we manage it? The second side of the safety has to do with safety for human beings. So most of these parts have voltages and currents that are quite hazardous to human people. And how do we protect people from that? How do we protect our first responders when they get on site, be it to a battery fire or a vehicle that's sitting there with a battery in it that can cause serious damage or death to a person? So we have safety circuits in there, and those are also changing, and those standards are evolving. So we look at testing itself. There's a few things that we kind of have. They're kind of de facto standards we find in the industry. We've got the state of charge, and this is a big one. You know, how much current is in the battery? How much power can it deliver? How much is remaining? And so that one gets tracked a lot, and everybody kind of looks at that, uses that in different fashions. The state of health is a little more nebulous and a little bit harder to define. It's more some of the monitoring we were talking about with respect to the safety and the monitoring of the individual cells themselves. In terms of, do I have certain cells that are degrading faster than others? What is the expected lifetime of this? What can I use of that data that might help me determine what the expected lifetime is? And so there's a set of tests for that. Leak tests, most of these, we find two different types of leak tests that occur in general. We find that we leak test coolant circuits where we're using a liquid of some form, or a fluid, I should say, of some form, in order to maintain a moderate temperature in the batteries. Additionally, we also have the enclosure that the batteries might be placed into in order to determine that they will not off-gas out, or more importantly, even to take things in ingress. For example, if the battery to be plunged into water, what happens? How long can it handle that? And then last or not least, and this gets into more what people typically tend to think about for battery testing, is the charging and discharging. And this gets down into what voltages and what currents do I put into the battery, and what information do I get out of that when I do it. So it kind of tells us a little bit about what we have to do. These things are all changing. This presents the shorter time frames present some difficulties for us in terms of what we're doing on these parameters. And the shorter time frames sometimes would mean adapting laboratory and design validation methodologies into high volume production processes, because you haven't figured out exactly how you can test this efficiently in a production environment, or perhaps what are the key parameters I really need to test in the production environment versus what's done in order to prove the things that you want to prove back at a product design point. And we see some issues with this in testing today. We find that those tend to shake themselves out over time. Once again, that goes back to the traditional way of doing these things, and you might have had the time up front to do that. Maybe now you have to go into production with what you know and be able to scale back to something that is what you need in order to prove that you built these correctly. Sometimes we find some difficulty in separating product design validation parameters from production testing parameters. And it gets into the same thing in terms of what's important at the end. Sometimes you find out that the things that they were doing in the laboratory are very important. You need to do those in production. But how do I put laboratory equipment or laboratory equipment measurement capability into a high volume industrial application? Overshadowing all of this, of course, is that potential for change. And that's the thing we're looking to try and deal with and handle and be able to have a basis that we can go forward and be successful in terms of what we're doing. This is what we have to do in order to handle our testing. Next slide. So this slide talks about end-of-line testing, right? And end-of-line testing is traditional. This is what we know, right? And this is the test we do once everything's all put together, and this is what says ship the part to the customer. And the issue with this, if you do just end-of-line testing, this can be a problem, especially for some of the battery packs that we're looking at today. They are very large, very complicated, and very expensive devices. If we wait to the end of line to test them, we have a lot of value that we've built into there. And it's very costly to reject at the end of the line. As you move upstream in the process and you have less and less value in the part, there's less risk to waiting a while before you do it. But that gets us into an in-process test, which is the next slide, which tells us what are we going to do in order to qualify this as we go so we don't have to pay that big price at the end of the line. So in-process test means is I do a little work on the part and I make sure I did it correctly. And we test it and validate that the assembly processes prior to where we're doing our testing are good, and we should continue to put value into this part. You do this, you're going to get a greater first-time capability at the end of the line. Reflecting back to the last slide, we want at the end of the line to have no failures because the costs are so high. By putting this in-process test in here, we can identify issues sooner and earlier in this value stream. And this can provide some feedback to correct the defects and the issues in the build process. The sooner you catch it, the sooner you correct it, the more good parts you have in your process line. And by doing that, you minimize scrap and rework, and you're going to maximize some uptime and some overall equipment effectiveness. So in-process test enhances the end of test, the end of line test. And to succeed, you need to have both a combination of in-process test and end-of-line testing. A key way to deal with this convergence of the battery technology and the timing and the large, quick ramp-ups is to use the same test equipment and the same test equipment supplier for both your in-process test and end-of-line test. If you can do this, you're going to get a single point of contact for all of your test functions, and dedicated engineers will understand the part through its build process. By doing this, if you got these dedicated engineers, they have a deeper understanding of the part characteristics and how these design changes that are going on can affect the test process. Sometimes things aren't very obvious. Some changes will not affect the testing or won't change what you need in order to do a valid test. May change test requirements, but you don't have to change your hardware. You just have to reflect in the new differences. But that's something you want to evaluate as you're evaluating these changes. Additionally, if you've got a single point of contact across both inline and in-process, end-of-line and in-process, you're going to have easier test data flows, management, analysis. So ATS is a good example of a company that does both the in-process and end-of-line test. And I might also add that doing this can also reflect to the assembly people as well. So we talked about finding these close relationships in order to be able to respond to the changes and integrate these changes quicker. And ATS can do that as well with the assembly process as well. Next slide. So getting into the actual test process itself, we're going to take a look at that now. Let's talk about this for a little bit. Okay, so the first thing we should do is break some of our existing production biases. And I only say that you look at battery pack manufacturing we're using, for example, we're beating up on battery packs today, but this applies for other operations, or I'm sorry, other parts that use lots of batteries. Grid storage is an example that you might also apply in this particular case. So what gets me is, I call it the part process funnel. We start out at the beginning of the line with the need for large quantities of parts. And up here, we may have to be processing parts at a parts per second kind of rate. And in the little pictures here, we show the formation process starting at the left, and then we get to a cell. It could be a pouch, could be a prismatic, could be an entity that we're pouring the electrolyte directly into and doing it that way. The formatting and packaging changes based on your applications. At any rate, we start gathering a bunch of these because the voltage from a single cell and the current from a single cell is usually not applicable in the electric vehicle market or in the grid storage market, some of these other applications. And so we start combining up a bunch of batteries, and we start putting those into some type of module. Terminology changes. Sometimes we see module, sometimes section, sometimes array. But at any rate, I think I'll tend to use module here, but kind of reflects into the modularity we're looking at. And so I'll use the word module. So at the modules now, we're starting to look at how many seconds per part. And that's because I've taken maybe, if we look at our array here, I've taken maybe 6,000 of the battery cells and interconnected them all and placed them in something, right? And it's like, okay, now I've gone from seconds per part to, from parts per second to seconds per part. And then when we start putting our modules together, I get a bunch of modules, I put them into a pack, and we get down to the end of the line, we're looking at minutes per part. And so the velocity of the line just kind of changes as you go through this whole process. And additionally, it's not quite that simple, of course, because some of these processes are continuous and some of them are discrete. When it comes to discrete manufacturing processes for some of the markets that we're going to and some of the producers that we're going to, we're used to things being discrete. I do a single event and then I move on to the next, and I kind of gate it all at the same time. We look at things, especially up in the formation process. I have things that take hours or days to complete. And so I take my parts and then they kind of sit at a single process for a long period of time. As we move downstream, this occurs also. We see that sometimes in some of the thermal materials or sealants where we need curing times and whatnot. So I spread down the materials, and then I have to wait or I have to cure them. And so once again, I go from this thing where I'm trying to get parts at a minute per part basis, and suddenly I have something that needs to sit there for 30 minutes. So this causes some grief in terms of trying to use our traditional tools for how we do this. Additionally, as we go down the line, the part handling changes. There's many physical changes. And we're reviewing all this because when we try and do our testing, we're trying to come up with something that's going to help us and work and run all the way across the board here. So we look at our part physical changes. We start out at the beginning with small parts that are small, they're light. And by the time we get to the end, they're very heavy and very large. And so our part handling changes. And we look at our part connections. We start at the beginning. We've got lots of very dense, very small things to put probes on if we want to measure voltage. For example, on our cell, we've got little tiny areas we have to hit. And if I'm doing parts per second, I'm going to be doing that by doing large arrays of these with very dense measurement connections, very high measurement speeds. And then as I move down line, my number of connections starts to get lower, but the magnitude of the things that I'm measuring starts to increase. And we see that as we go on down the line. So we get to the end, we have very few connections at the end, but they're very large because at this point we've aggregated the power. And the little circles on the bottom are trying to show the power aggregation. We start out with nothing. As we go down the line, the amount of power we're looking at starts growing and growing. And this is another thing that we have to deal with. And sometimes when we try and come up with solutions for this, that the active power on there is going to prevent simple solutions because we have to take that into account. What does that mean to us in terms of what we're doing? We look at all these different connections, and we're looking at, how do we scale things? How do we handle the changes? We have to look at manual versus automated connections to our test equipment. Traditionally we'd start out at development and pilot and high volume, and now we want to perhaps look at some tooling that I can use and keep reusing as we go across the board here. So break some biases, look at this a little bit differently, start looking at the big picture because it has an effect on us if we want to be successful. Next slide. So here it is. Battery testing is not just testing a battery. And that's because ultimately we're testing some very complex systems. So we look here, kind of highlighted some of the things that are involved in these systems. So certainly there's a battery. Actually, there's probably thousands of batteries in there, and they all do need to be tested. But we also have to take a look at all these other things kind of listed, a bunch of different things in terms of the welds and the connections and structural integrity and what's the actual fluid, the chemistry of the electrolytes we put in or whatever is the formula within the battery cells, what safety systems are inherent within our part, what kind of diagnostics are there. And so if we look at this, the assembly validation uses a wide range of existing technologies, and it gets applied to many different scenarios. For example, the welding, welding here, we start out, and typically when we start out on these, we've got the interconnection of the batteries, right? And that can take several different forms and formats, and it's usually high speed and very dense. We also need to consider the structure that the batteries are going to be placed into. And lots of times this is a non-rigid structure early in the assembly process. And then as it goes down the process, it becomes more rigid. We have the interconnection of similar sub-assemblies. And what does that do? We have to test those interconnection points. Some of the things we're looking at might be associated with technology crossovers from other industries. So for the electronics, we talked about the high density connections. Maybe we need to look at the electronics industry to see what comes out of those, the tooling in those industries in order to make a large contact, lots of places in very small areas. Maybe we need to look at some of the electrochemical type systems in terms of measuring what it is within the battery that helps us. And actually some of that has come over. We'll bring that up. We take a little deeper look at the tests themselves. And once again, then we have to separate out what's required for validation versus testing. And in this case, validation means that I did the job correctly. Testing kind of means that it's doing it correctly. And once again, safety considerations might overshadow some simple solutions. So moving on to the next slide. Beating up on the battery pack once again. Here we have kind of a cutaway on a pack to kind of show some of these things. We talked a little general before in terms of bullets, but here we're looking at taking a little deeper look at some of these points. Within what we have here, we can see that we've got assembly validation and testing. And the distinction I'm making here is the assembly validations are things that are simpler and have limited data. So sometimes it's a go, no go. Things are where they need to be. Maybe a single measurement, limited. The things we have in green tend to be more detailed. You require more accuracy. You got more complex measurements. Sometimes you need stimulus and response type measurements. And sometimes in these things, you need to look at your variable data analysis. So you need to look at multiple things and see how they work with respect to each other. If you think about the slide we showed with the parts going on through the process where we started out with cells and got the modules and packs, you'll see that we have similar measurements that we're using as we go across these things, but the magnitude is increasing as our process progresses. Some highlights to consider, for example, structural integrity is both a mechanical and an electrical issue where we need to test this for ground bonding or isolation. Our leak test can be both the coolant channels and the pack enclosure. However, the packaging is put together may require additional sectional tests in terms of how things are built in there. Maybe I got separate containers, or the battery pack is broken off into essentially 3 separate batteries within one, or here are the variations coming in that you have to deal with. We look at charging and discharging, so it's voltages and currents. Once again, we start out with the many channels and end up with the many channels, the small voltages and currents, and at the end of the line, we've got a few channels with large voltages and currents. And our test strategies and currents and durations for both the charge and discharge can vary depending on where we're at. And there's a lot of variability that occurs on that. Inherently goes into the product itself and the chemistry that the product is based upon. So all of this additionally has smart parts associated with it, the battery management system, and the communications associated with that. And so how do we deal with those computers? We tend to get off in the software world a bit, but ultimately we're going to physical things. We shift from the analog world to the digital world, but nonetheless, that needs to be handled as well. And so all the timing and technology impacts, all the changing, it impacts what we're doing, trying to figure out how to test this. Overall, one way to try and protect against all these changes is perhaps to use high accuracy equipment of the same manufacturer, something that I can use even as I upscale my increased magnitudes and measurement capabilities. So I've got enough accuracy to be able to measure the low end, but enough capability within it to measure the high end. Components that are scalable are good. So for the power and the charge and discharge, if I need to do something at a 60 amp rate at one point, and I want to take that up to a 600 amp rate, can I use the same base power modules and stack extra modules on there in order to build that up? Minimize the amount of spares that I have and the familiarity of the systems and your people in terms of the equipment that you have in there. Another thing to look out for is configurability. What is it within the equipment that I have that I can use to reconfigure, perhaps repurpose? It's like the testing I was doing was great. It was getting me good, but on this newer part, I would need to change that a little bit. I want to make sure I can change that. So these are key things to consider. So let's get into actual testing. We kind of set the frame, talked about what the requirements are. So let's move on to the basics of test. Next slide. So the basics of test for battery are fundamentally the same as they are for any testing. And there's a few that we key in on. Ultimately, the physics are the same. We're looking at electrical characteristics, and for the most part, that's just purely measurement. We've got power, and we're putting power in or taking power out, and that is control and measure. We've got leak tests. The leak tests vary tremendously in terms of technologies that people deploy based on the leak rates we're looking for and the size. The large electrical packs are very challenging due to the large volume that are enclosed. And then, of course, the data acquisition system in terms of collecting this data and analyzing it, making the pass-fail kind of considerations at the end of time. So anything that we've got from our past history, things we've been using before, all apply here. And ultimately, the physics isn't changing. It's just what equipment do I need to implement this out? And so let's move on and take a look at what some of the tests might actually be. Next slide. So take a look at parts and tests. And I've kind of broken it down into a cell, a module, and a pack. And this goes across any conglomeration where we take a single a single battery cell of whatever format, and then I combine it into other combinations in order to increase the amount of power that the ultimate product can have. So if we go down the list, and these are typical, so we've got high pot insulation. You'll see that runs across everybody. Where you do it and when you do it based on how you build this and how it's packaged up. So these are typical safety type tests that are done on all electrical devices. Open circuit voltage tests, voltage measurement, predominant. And we can see that's across the board with the increasing magnitudes as we go downstream. Direct current resistance, DCR, we also see ACR, which would be AC current resistance, and effectively measuring the battery impedance. And what's done, and where that's done, and how that's done, lots of times it's done with a pulse. Sometimes it's done with a pulse at a single, it's done with a frequency, which would be the AC case. At any rate, we're ultimately getting an impedance reading out of the battery, and it's something that should be repeatable, and it's something that can tell us about the battery, especially if we get into sweeping frequencies in the AC world. You will find that's across the board here, once again, with increasing currents and voltages as we go downstream. Then we have charging and discharging, the basic capabilities, the basic functionality we want out of the cell. And what sequence we do that product, function of the product itself, and what its capability should be. Then we start getting to things that start adding on in terms of the complexity. So low voltage systems, this would be the other things that are on a module or a pack where I've taken a group of batteries. So this sometimes would be your intelligence systems, your battery management systems, things that are measuring the individual state of charge, voltages and temperatures of cells or packs or modules. This could be integrated functions for safety. So things that we call them low voltages, 24 volt, 12 volt, things that are more typical control type circuits. And between the module and the pack, similar kind of things, except increased requirements on the pack because there's a lot more functionality when you get up to a pack level. Leak test across both. And then what really is reflected here when you get up into the pack, not only are you checking the pack, you're also checking interconnections if you put a bunch of modules into a pack. And then high voltage interlocks. Typically we find those at the end because as we string these up, we tend to start getting up into the higher voltages. But that's at more of a system level. You're providing a pack that's got a system and it has capabilities in there for enabling and disabling the electricity in the whole from coming in or out of the part. So this is basically the tests that are done and what's done. And the trick for us is the magnitudes, the currents, where in the process line, how we do this. Take a quick review at the different parts and processes and go to the next slide to do that. So at this point here, we're kind of looking at the very beginning. So we talk about cell tests, and this is back in the beginning. We kind of split it out. We've got formation when we're actually making the battery be a battery, or incoming incoming production on a bunch of cells. So kind of state some typicals you might find in terms of the cycle time. Formation is highly variable, but it takes a long time. It's variable. It's hours to days to make it to form a battery. And typically we're dealing with charge and discharge, open circuit voltages, and DC resistance. The formation, typically we might see that we're doing charge and discharge around 5 volts, 10 amps. Typical, the numbers go for the currents go up and down based on the size of the pouch, the cell or prismatic, whatever it is that you have. You know, what's your power density is going to determine what that is. We kind of split it out. We've got formation and grading. Formation is what really makes the battery a battery, and grading is kind of like your end-of-line test to prove that it really is a battery and it's good for the next step in the process or the next part of the production. Once again, same kind of things are done, just different rates and charges and stuff. Production cell tests tend to be incoming inspection. So now that I've got a bunch of cells, perhaps they came from a different facility, perhaps they came over on a boat, they've been sitting in a warehouse for a month. Finally, they come on in, I want to make sure that they're good. And so take those batteries, take an open circuit voltage measurement on them. If you have information in terms of what the voltage was at the time the battery was shipped, lots of times you take the measurement now, do a comparison between the two, give you a real good indication what the discharge, self-discharge is on a battery. Great test if you got the information. Moving on from cells, now we're going to start taking a bunch of cells and put them into modules. So let's look at the module tests, which will be our next slide. On the module tests, once again, we have the same kinds of things we were looking at before. So typically, cycle times are in minutes. We bring in some of the HiPod testing and whatnot. Here is where we typically start to see this for isolation or earth bonding, because now we're starting to get an assembly. It's got some structure to it, got some parts and pieces to it. We'll typically do charge-discharge tests. Low voltage communication tests now come in. So low voltage circuits, if you have them in there, if there's things that you need to some stimulus to simulate what's going on with the interconnections at the next higher level. Sometimes you have to provide that here. Typically control signals. Sometimes it's in the communication signals. Coolant circuits typically here are coolant only and not necessarily enclosure. And kind of take a look at the things that we do in terms of the functionality now, because it's not just a single cell anymore. It's now a collection of cells. The power ranges here vary considerably based on the size of the cell, but typically we tend to see them in the 10 to 40 kilowatt range, and the voltages are also all over the map as well in terms of what it is and how many amps you get out of it. So here again, your equipment's got to be sized in, and if you think there's a lot of change going to be occurring in your parts in this product, this is an area to watch out for, and this could well be. The trend that we're seeing at this level is more monitoring and control. So at the sectional level, things are getting smarter. And we look at that, things getting smarter. The communications at this level are typically a CAN, but we also see ISO-SPI or other lower level communications here, as opposed to when we finally get up to a PAC, it's typically just a CAN or a higher level one. So that has to do, well, there's a lot of reasons for that. But at any rate, if you're going to do testing, you need to interface at the level that it's at here. If it's an ISO-SPI type connection, then you're effectively mimicking what the overall battery management system is going to be doing. Additionally, lots of times at the module test level, now since we're starting to do some charging and discharging on the part as a whole, we may need to leave the modules at a given state of charge as a process down the line. And this could be a real safety issue, and you may want to do that in terms of how it is that you go about building your parts. Next slide. So now we're moving on to our final product. And so here we've got our package. This is what we're going to send to the customer, to the end user here. And now we've got a part that's going to take minutes to test. And it's got the same types of tests we had before in terms of perhaps we need to do some more isolation safety type testing, because we added some more in terms of bolting together structures. And now in the power, the charge and discharge are typically the largest that we're going to see in our systems. One thing I might note here, you got to be careful on discharges in terms of how you're doing that, in terms of what your facility can handle in terms of the electricity that's discharged. Most of these systems we like to have regenerative, so the power we're putting in, we're using when we take it back out. If you can't use all the power, then it needs to go somewhere. The low voltage communications, now we're at our maximum level in terms of what they are. We may need to simulate portions of the end application in terms of dealing with this, especially with respect to the high voltage interlocks. Leak tests, lots of times now we've made all the connections we're going to make for all these circuits and the coolant circuits, and now's the time to test them all, or at least at a minimum we have to prove anything that's come on past the interconnections in the previous step are good. Functionality here is at its most complex level. Anything in terms of switching, changing, interconnecting, shutdown, safety, this is the place to prove that it's all correct. What we're seeing at this end, Like I said, it takes typically minutes to test these things. Charging can be time consuming if you're going to have a large discharge on this. Sometimes you want to discharge to a point and leave a given state of charge when you ship it. Power ranges here, wide disparity in what's out there in the market, but we see things typically from 80 to 600 kilowatts, voltages 350 to 950 volts, amps 200 to 1800 amps DC. So we see a lot of variation, usually based on how many modules and what the end application is. And the trend here is higher voltages, more monitoring and control. And so the higher voltages, the supply chain for the power electronics is responding in terms of new designs to be able to handle the higher voltages. Product is out there and it can be done, but it can change things. As the voltages go up, you have to look at your cabling, some of your systems, and once again, back to your measurement systems in terms of what they can handle. So moving on to the next slide, I think we're going to let's see if we can't put this all together. So when we look at battery testing and what is our value in terms of what we're doing here, and I always like to say testing is usually considered a non-value added item. Not always. Once in a while we do some calibration or whatnot, but typically it's non-value added. But that's what we're looking for. The numbers vary, but I think it goes somewhere like this. Our testing is really catching that small percentage of parts were built incorrectly, and part of why we put the in-process test is there when an assembly process goes out of control, we want to catch it as soon as possible. So by the time we get down the end of the line, we've got nothing but good parts coming off of there. So we're really looking for those ones that messed up or we had a problem in our process. The thing is, although there's no value added, the value of or what the cost is reflected back on you as the producer, it gets larger and larger as you go out. And that's kind of what this graph is trying to show. You catch things in line, it costs a little bit, blah, blah, blah. By the time it gets out to your end user, big cost in terms of the impact of a single failure. The cost of a single failure reflects and pays for a lot of the test capability in the lines. Next slide. So just to sum it up, traditional production testing, this kind of shows what we typically have been used to. You come up with an idea, you go through a prototype, you get it commercialized, you get ramped up to full production, things are just cruising, you crank the part out, you get into a continuous improvement cycle. And this took some time. And right now we've got our time compressed, and that's kind of what we're showing here. And part of the idea of the little graphic with 1 hour, 1 day, 1 week is how long it takes you to respond. This is the issue. As you get deeper into this, it takes longer to reflect your issues back into the part. And that's a challenge that we have, okay? It's like the things that we used to uncover in commercialization stage or in the production stage, we had some time to get it fixed, right? And now what we're trying to do and what I'm trying to say is it's better to spend the time up front now to try and figure this out in order to help us shrink this down. So what are we looking at today? So here's kind of what we're looking at today, right? And so you can see we've got the real steep slope and we've got things that are on top of each other. And so let's remember our shift in perspective, right? Acquire and apply our domain knowledge that we have inherent in our own companies and go get help where we need it. Take our proof of principles, our lab to pilot to production line, right? So this is, a lot of cases, this is like right on top of each other. And so the idea is to identify issues and problems quickly. That is, let's solve early for failure. How do we do that? In terms of what we're going to do this with, we can look at equipment that's purposed to flex from the pilot to the production volumes. For example, the little pictures on the left kind of show kind of like a development idea, some prototype tooling where the prototype tooling is built such that it can be rolled forward into what you see at the bottom, which is final high volume production. And additionally, the amount of parts that could be built went from a one-off to many to thousands. And these are some of the things we've got to be thinking about to try and incorporate in the testing. And while we're doing this, though, we also have to be looking at the items that are on the right side of the graphic in terms of what it is that we're using. So what are the next generation processes that are coming out in terms of, our digital modeling, in terms of artificial intelligence? Is there anything I can apply? We talked way back in the beginning about the state of health. What things do I need to measure in the production process and guarantee me a long state of health on these batteries? How do I even begin to figure out what that is? Am I measuring it today or not? Those kind of things. Some ways we've got, some safety issues, right? And how do we handle these parts, especially as the power is growing and growing? And then facility management. What do I have in my production plant? Can I handle the electricity that I need to charge? Can I handle the electricity that I might regenerate? How are we doing all that? Got to be looking at that early on. You don't have the time to wait. Some of the things, especially in the facility, things take time. Especially if you're looking at large scale, it could be big equipment, tough to get. And so we need to look at these things in order to implement them for our success. Looking at equipment flexing from pilot to production is big. The scalability is big. And then making sure you take a look at what your existing facilities are to make sure that they can roll with the changes that are going to be coming at you. Next slide. So ATS is uniquely suited to provide solutions through this entire life cycle of a product. And, we've got really good people that work here, and we've been doing this for a while, and we make really good machinery. We've got a great team of project management to make sure that these programs get implemented correctly. Some of the phasing, staging, especially if you look at ramp production or integrating things that will support a pilot, and then how do I build that up and upscale that into a large volume production line? What can I do to do that? How do I do that? These are the things that we're good at doing for you. We're everywhere around the world. We can help you no matter where you're at. And we've been around for a while, and we're pretty darn good at this. Next slide. You heard me talk about we're good. Here's just a couple examples to give you an idea of what we've been doing. We've been doing batteries for a long time. So we got in the game early, and we enjoy doing this stuff. We've done a lot of it. We've been going through, changing as the products have changed. So the baseline that I presented to you here is coming from our experience in terms of what we've seen changing, where we think things might be changing. So we like to say at our place, every day matters, today matters. Tomorrow matters. And I hope you have a good day. And I appreciate you listening to me today. Take care. And with that, I'll send it back to Mary Beth.
Thanks, Jack, for that great information. That brings us to the end of our webinar. If you learned something from the session, please tell your peers about it. The recording will be available at autonews.com/webinars. When the webinar ends, a survey will pop up on your screen. Your feedback helps us create future webinars that are even more beneficial to you. Thanks again to Jack and ATS Industrial Automation for bringing us this presentation, and to you for joining us. On behalf of everyone at Automotive News, have a great rest of your day.